Good day, everyone. I am Christine Joyce P. Bandilao.
I'm Akisha Quirante.
And today we'll take you on a quick but exciting journey into the microscopic world of atoms, where bonds are born and chemistry comes to life. Welcome to our presentation on valence bond theory.
Learning objectives. Number 1. Define the valence band theory and explain its basic principles in relation to chemical bonding. Number 2. Differentiate between sigma and pi bonds based on orbital overlap. Number 3. Explain the concept of hybridization and identify the types with examples. Lastly, number 4. Demonstrate understanding through solving exercises, constructing molecular models, or drawing orbital diagrams.
So let's start with a big question. What exactly is valence bond theory? Imagine two lonely atoms floating in space, each one holding a half-filled orbital, like two hands reaching out for a handshake. When these orbitals overlap, they share electrons, and voila! A covalent bond is formed. This magical overlap happens when orbitals from each atom occupy the same region of space. The electrons spinning in opposite directions attract both nuclei, forming a stable bond. And here's the fun part. The stronger the overlap, the stronger the bond. So in chemistry, as in life, connection is really everything.
Gilbert and Lewis. Lewis contributed the electron pair bond from his paper called The Atom and the Molecule in 1916, proposing that a chemical bond is formed by a pair of shared electrons between two atoms. He also introduced the octet rule, suggesting atoms bond to achieve a stable, noble gas-like configuration of not 6, not 7, but 8 valence electrons. He developed the use of Lewis dot symbols. Again, Lewis dot symbols, which represents the valence electrons of an atom as dots around its chemical symbols. Walter Hettler and Fritz London. Quantum mechanical explanation of the covalent bond, atomic orbital overlap. Walter Hettler, along with Fritz London, laid the quantum mechanical foundation for valence bond theory in 1927 by applying quantum mechanics to explain the covalent bond in the hydrogen molecule H2. They used the Schrödinger wave equation to show how two hydrogen atoms could form a covalent bond by sharing electrons, an idea previously only theorized by Gilbert and Lewis. Their approach, now called the Hettler-London approach, described the formation of a bond as the overlap of atomic orbitals between two atoms, where the electrons in the bond are attracted to both nuclei.
Now, let's meet the man who gave a valence bond theory its modern form, Linus Pauling. He's the one who connected the dots between quantum mechanics and chemical bonding, making chemistry more understandable and beautifully logical. Pauling introduced the idea of orbital hybridization and resonance, concepts that explain why molecules look and behave the way they do. In 1939, his book, The Nature of the Chemical Bond, became a landmark in chemistry, shaping how scientists view molecular structures even today. In short, Linus Pauling didn't just study bonds, he bonded chemistry and physics forever. John C. Slater, another brilliant mind who took bonding to the next quantum level. He developed the determinantal method, a fancy name for a way to handle multiple electrons using math, while still obeying the Pauli exclusion principle. Together, Slater and Pauling formed the dream team of chemistry, building a general theory for how atoms unite into molecules. Slater also helped define hybridization and resonance, showing how orbitals blend and how structures like benzene can exist as a mix of forms. Basically, if Pauling was the storyteller of chemical bonding, Slater was the mathematician who wrote the language it speaks.
The two types of bonds. Sigma bond. A sigma bond is the strongest type, formed by a direct, head-on overlap of orbitals along the internuclear axis. Pi bond. A pi bond is weaker and forms from a side-by-side overlap of orbitals, occurring in multiple bonds in addition to the sigma bond. Sigma and pi bonds. Sigma and pi bonds are two types of covalent bonds distinguished by how atomic orbitals overlap to form them. A single bond consists of one sigma bond. A double bond has one sigma and one pi bond. And a triple bond has one sigma and two pi bonds.
Now, picture this. An atom as a DJ, mixing orbitals like beats. It blends S and P orbitals to create brand new hybrids, perfect for stronger bonds. sp gives us a linear, sp2 gives us a trigonal planar, and sp3 builds the mighty tetrahedral. Hybridization, chemistry's ultimate remix of nature. We have different shapes: linear, simple, and straight. Trigonal planar is like a flat triangle. Tetrahedral, a perfect pyramid of balance. Pyramidal, slightly tilted with a lone pair twist. Trigonal bipyramidal is like a stretching in 5 directions. Seesaw and T-shaped, because even molecules like to mix things up, yes. And finally, octahedral, symmetry at its finest, with 6 bonds around the center. Each shape tells a story about how electrons arrange themselves, a little dance of balance and geometry. Let's learn hybridization the fun way. The organic chemistry tutors got you covered. Click and let's roll. Time for Professor Dave. Quick, clear, and cool. Click to learn hybridization's magic. And that, dear listeners, is valence bond theory, where atoms meet, mix, and form the foundation of everything we see. Thank you for joining us. And remember, in chemistry, every bond begins with a spark.